Okay, welcome everyone. Today, for the first talk, we will have Eva from Case Western Reserve University to tell us the deformation of Borel-equivariant homotopy theory.
All right, so thanks for the invitation and thanks everyone for coming. So I'm going to be talking about some joint work with Gabe Angelini-Knoll, Mark Behrens, and Hana Kong. So this is a talk about synthetic homotopy theory. So I want to start by giving an introduction to what that's all about, and then I'll talk about the motivation for our problem, which is about understanding this for C2 homotopy theory. Okay, so the slogan for synthetic homotopy theory is it's a way of producing interesting contexts to do homotopy theory that are equipped with a good comparison map to classical spectra. So suppose you have some spectral sequence. So I'm going to be very vague in this intro part. So I'm just going to say I have some spectral sequence and it comes from some kind of tower. So if you want to make precise statements, then maybe this needs to have more conditions on it. But so far, I can just write down like a tower of vibrations. So a spectral sequence is or at least it comes from some kind of tower. And in this theory, we're actually just going to focus on this row on the top. So I'm going to think of this as a filtered object. And okay, so X1, X2. And if we're working in some category C, which, you know, we'll probably have some kind of conditions on it later, then this filtered object is going to live in the category of functors from some kind of poset category. Okay, so well, what I wrote is something indexed in natural number indexed, but what I actually mean here is Z with the just with the natural poset structure. That means if I want this to be Z indexed, I can always continue it to the left if most of my motivating examples are bounded though. Okay, so the setup for synthetic homotopy theory is roughly, how do we produce an interesting context for doing homotopy theory? We start with a spectral sequence, which we're thinking of as an object in this category. And then we're going to produce a new category, which is constructed using the information of the spectral sequence, called a synthetic category. So now is the point at which I might want some kind of multiplicative structure. And you'll see in the examples that there's no problem with having a good multiplicative structure in the examples we care about. So the kind of category I'm going to construct is, let's look at modules in the category of filtered objects over this thing X. So if X is a good multiplicative structure, this is a thing I can consider. Okay, so why on earth would I want to do this? Why does this capture anything about the information of the spectral sequence? So there's a motivating example. So if I start with the Adams-Novikov spectral sequence, then the claim is that I get something related to C motivic homotopy theory. So there's one more technicality I need to put in here in order to actually make true statements. So we want a variant of this setup. So if I have a filtered object, say X, then I want to actually talk about a shift of it called the décalage. And the point of this is that if you do this construction to the filtered object, then the corresponding spectral sequence is going to have what's called a page shift. So the ER page of the décalage is going to agree with the ER+1 page of the original spectral sequence. Okay, so now I can talk about the motivating example. So if instead of looking at the Adams-Novikov spectral sequence, if I look at the décollage of the Adams-Novikov spectral sequence. So just as a reminder, this is, it's the Adams spectral sequence based on MU. Maybe I'll say it's the MU Adams spectral sequence. So this comes from a tower that looks like a bunch of copies of MU smashed together. Its E2 page is X'd over MU smashed, MU star MU. And this is a very well-known and liked thing. Okay, so if I look at the décollage of that spectral sequence, it turns out that the synthetic category you get associated to that is cellular C-motivic spectra. So, and there are a couple of adjectives I'm missing here, so you definitely need to complete it too. Okay, so cellular C-motivic, 2 completed spectra, and everything is going to be p-complete because we're dealing with spectral sequences, and I'll just omit that. Okay, so this is a result proved by so I'll put a bunch of names here. So Georgi, Krause, and Isaacson Ricca. Georgi Wang Xu. Okay, so this is very surprising, and the idea is like, well, you know, I'm not going to say too much about C-motivic homotopy theory, but the idea is like it's a category that's built instead of building a category using simplicial sets. You know, there's a construction, you start with simplicial sets and then you get spectra. Instead of doing that, you can start with simplicial schemes over the complex numbers. And this is a thing that algebraic geometers cared about, and then homotopy theorists got a hold of it, in part because it's a category that has a lot of relationships to ordinary spectra. There's a comparison functor, and a lot of computational mileage was gotten out of this by Dan Isaacson and a number of other people. Okay, so the downside of motivic homotopy theory is that it seems like you need to know some algebraic geometry in order to be able to say anything about it. And what this theorem is saying is that you can actually ditch the algebraic geometry and just study the Adams-Novikov spectral sequence. So this is pretty amazing. I want to talk about a generalization of this, or really like this idea in a different context. So the next result I want to mention is, well, what if instead of doing the Adams spectral sequence or the MU Adams spectral sequence, let's work in C2 spectra. So in C2 spectra, there's a thing called MUR that's like if you have MU and then you notice that it has a natural C2 action on it. So you have MUR based Adams-Novikov spectral sequence. What you get, it turns out, is okay, so roughly it's R motivic spectra, and then instead of cellular, I have to put this other adjective, so ardentate. So this is what this means is that this is R motivic, again completed, and I'm not going to write that. Spectra, so it's things built using schemes over the real numbers. And then if cellular means you're generated by spheres, here you're generated by the sphere and by this other object. So this is due to Birkeland, Hahn, and Sanger. Okay, so if you want to study R-motypic homotopy theory, what you can do instead is study the MUR-based Adams-Novikov spectral sequence. Okay, so there's this word deformation in my title, and I want to say something a little bit about what that means in this level of generality for these examples. So what I mean by deformation is say what algebraic geometers mean by this, where there's some parameter. So, say a deformation of a ring. It's you add a parameter, and if you set that parameter equal to 1, then you get out what you started with. And if you, but instead you have this family. So what is the deformation parameter? So the deformation parameter comes from the shift map. So people familiar with motivic homotopy theory will remember that there's a class called tau. In general, in these synthetic categories, if I have Y as some kind of synthetic thing, then I've got a shift map that just comes from the fact that a filtered object has a shift map. This leads to bigrading. So, for example, you get well, if your original theory has one grading, like you have singly graded homotopy groups, then the synthetic category will have doubly graded homotopy groups. I guess in my MUR example, if the starting category you have 2 gradings, then the synthetic category will have 3 gradings, and so on. Moreover, there is a functor from a synthetic category back to the original category this is built on that just takes the colimit. And we're going to call this invert tau. So those who are familiar with, say, C-motypic homotopy theory, it not only has this element tau, but there's a functor called Betty realization from C-motypic spectra to ordinary spectra. And concretely, what that functor does is it inverts tau. So this is just a more general version of that phenomenon that was already known. Okay, so lots of interesting categories. And one advantage of this is that this is computable. So I want to say a little bit about how computing homotopy groups in a synthetic category relates to the spectral sequence that all of this was built on.
Excuse me.
Yeah. I think like Doug has hands up, so maybe there's a question.
Oh.
So is this why, Doc, the diagram you drew at the beginning, which was something parametrized that looks like an Adams tower, is this the same diagram?
So Y, I mean, is an element in the is an object in the synthetic category. So on the right hand side up here, a synthetic category is something that's like one of these module categories. So Y is an element to the module category, is an object to the module category, and in particular, it is a filtered object. And so that's why I have this.
No, but the colimit of a filtered object, as you've drawn it, would just be the
oh, okay. Yeah, I'm sorry. So there's okay. There's a grading issue. Yeah. So it's like if you have a filtered object, depending on how you grade it, you can either take the limit or the colimit. And yeah, no, you're right. Sometimes people index these with negative gradings and then they go off to the left. Yeah, okay. So I guess in the one. Oh, wait. So No, so the co-limit of the filtered object I've drawn, that's not what I'm doing. It's the in this, so I guess if I can have a module over this filtered object that oh wait, okay. My grading got messed up somehow. So what you're supposed to think is that, like, say in the motivic category, the sphere spectrum actually has gradings for all z and not just for the positive. So I think this is the problem. So for example, the sphere will have will be z indexed in like a non-trivial way because the indexing will correspond to the weight. So the wth part in the filtered object that corresponds to the sphere, I think maybe there's a little bit of translation between the top thing and what you're actually taking modules over. So like for the sphere, I want to do something like take the mapping spectrum from this. So this is going to be the W thing in my filtered object. So I think there's a little bit more going on here than I'm letting on.
All right, thank you.
Okay, so I want to say how to compute homotopy groups. Yeah. So by the way, this is the construction of Georgi, Isaacson, Krause, and Ricca. So under some hypotheses, so for example, Adams type filtration, there is a nice functor nu from in the other direction of my quote unquote Betty realization functor that so to justify the word nice, I'll say in the motivic case, it's something that sends the sphere to the sphere. It sends mu to MGL. So it's it magically picks out the correct motivic analog of all of these classical spaces. So there's this functor, and moreover, there's a spectral sequence. So suppose I want to compute homotopy groups in this synthetic world on something that's in the image of this functor. Something in the image. So what does the spectral sequence do? So in order to understand the spectral sequence, first you run the original spectral sequence for Y, but this spectral sequence computing synthetic homotopy groups is a variant of it where given a differential in the original spectral sequence, you're going to get a differential hitting some power of tau times Y in the synthetic. So, if in the original spectral sequence, if there's a differential X hitting Y, then both X and Y are killed in the spectral sequence. But in the synthetic version, X is killed, but Y and Y only becomes tau torsion. It does. So somehow the idea is that the synthetic homotopy groups remember not just the outcome of the original spectral sequence, namely the original homotopy groups, but also some information about how those homotopy groups came to be via the spectral sequence. Okay, so that's what I want to say about the general setup of synthetic homotopy theory. So by the way, this is a 45-minute talk, right?
Yes, 45.
Okay. Okay, so let's talk about this in an equivariant situation. So we want to extend or understand in a different way the results of Brooklyn, Hahn, and Sanger about deforming the C2 equivariant category. So, so far, what we have is that cellular chemotypic spectra is a deformation of spectra. And these armotypic spectra is a deformation of C2 equivariant spectra. And so a natural question is, what do I put in the left in order to get, so the next easiest thing I can ask for is just CP for P odd. I'll just briefly say why should we care about this? This is an interesting category, so this is hard. So for example, there's been some you can compute the Steenrod algebra, and the Steenrod algebra is really complicated. It's not flat over the cohomology point. The Steenrod dual is not flat over the cohomology point. There is a comparison map that would give an interesting way to, so from whatever thing we figure out how to put here back down to this would give an interesting way to study CP spectra. So, why can't we just mimic Brooklyn, Hahn, and Sanger's construction? So the issue is that their construction uses MUR, and there is no known CP analog of MUR, and this is a very hard problem. So the main idea in the work that I'm talking about is that this issue goes away after Borel completion. So MUR, I don't know how to make a odd primary analog of MUR, but the claim is that we do know how to make a Borel-equivariant analog of that. Okay, so I want to say a little bit about Borel completion. Okay, just to be clear, G is finite, really G equals CP. That would be interesting in its own right. Okay, so we have genuine spectra, but we also have Borel spectra. So Borel spectra are basically just spectra with G action. I can write it this way. So BG is the category with one object and achieves orthomorphisms. Usually what you care about is the genuine equivariant category, G orthogonal G spectra, and those are, for example, a good presentation of genuine G spectra would be indexed on G representations. Okay, so there is a comparison. So I can either think of Borel spectra as its own not quite as good category, or I can think of it as a subcategory via this inclusion. So this sends an object to just the mapping space. So this is often known as the Borel completion. So I can either think of Borel spectra as its own category, or I can think of them as the quote unquote complete objects in the genuine category. And a very explicit way that we can think about this as completion is if G is CP, then this is literally the completion with respect to A, where A is the inclusion of the fixed points into the reduced regular representation. Okay, so the claim is that the Borel-complete MUR atom spectral sequence doesn't require knowledge of MUR, and therefore can be generalized to other sorts of groups where we, in situations where we don't have an analogous notion of MUR. So I'll just sketch this. So the key facts here are so in the P equals 2 case, the cofiber of A turns out to be the same as C2 plus. So I want to reinterpret the MUR based atom spectral sequence in, after doing this completion. So the completion can be accomplished by smashing this cofiber of A spectrum together, and it turns out that it has this other form. So if I take MUR and smash it with just C2 plus, the shear map says that this is the same as the MU with the trivial action, smash C2 plus. So this is kind of the main fact. This is kind of how we get away with it, essentially, and why completion helps. So this, we're not quite there. This isn't the completion. This is something much more basic than the completion of MUR, but this is kind of the key fact. So this is something that you always have, this shear isomorphism. So even like in a G-set world, I've got a thing like that. So that's basically what we're using. So MUR. So let's start with the thing that we know something about. So my claim is that the MUR-based atom spectral sequence that has been Borel completed comes from this this object, and this does require some work to show that it actually is the right thing. So we show that this gives the same spectral sequence starting with the E2 page as the thing we want. Okay, so the point is that we can show that the thing on the left, well, it's not the same object as the MUR star plus 1, but after completion, it gives the same spectral sequence. If we care about the spectral sequence, that's good enough. So now we can apply this previous observation. And so then this is the, gives the MU smash C2 plus based atom spectral sequence. So the thing on the right is the thing that we can generalize. So this is one answer to the question of how do you generalize the completed MUR based atoms Novikov spectral sequence. What you can do is generalize this MU smash C2 plus based atom spectral sequence. So this is clearly something you can do at any group. And the stuff about deformations says that if if you, if you take the associated synthetic category to this, the claim is that if you take the synthetic category associated to the spectral sequence for the guy on the right, then you get the A completion of the Art and Tate R motivic category. So this isn't just a claim about spectral sequences. This is a claim about variants of R motivic homotopy theory, and it's a different way of building a variant of R motivic homotopy theory. Okay, so let's talk about this for CP instead of C2. So our theorem. So the first part is essentially what I already said. So how do we describe, I'll say generalizable. This is really the part we care the most about. Ways of describing this. So this is the R motivic category, or the part of the R motivic category that's generated by these two invertible objects. And then the point is that this is more understandable if you do the completion. So the first thing is the one we already said. It's the mu smash C2 plus based atom spectral sequence in so because we've completed, we're now working in Borel-equivariant spectra. And the other part of our theorem is that there is a different way that's more computable of approaching this mu smash C2 plus based atom spectral sequence. So the idea is that you can understand this by combining two other spectral sequences. So I'll say what combine means in a minute. So I'm combining the mu based atom spectral sequence with the homotopy. So this mu based atom spectral sequence, this is non-equivariant thing, or it's a non-equivariant thing that I've given a trivial action. So I'm combining this with the homotopy fixed point spectral sequence for the sphere. So I guess here we're I can do any of these spectral sequences to I can do the Adams-Novikov to compute the homotopy of your favorite space or your favorite spectrum. But the way these categories are built, you're looking at the Adams-Novikov, or these variants of the Adams-Novikov computing the sphere. So these two things put together, but really we like the second one more because it's more computable. We have a catchy name for this. So the non-catchy version is modified Adams-Novikov spectral sequence, and it has a catchy acronym, the MANS. So via the synthetic construction in the beginning of this talk, the claim is that if you start with the MANS as a spectral sequence, and then you do the synthetic construction to it, what you end up with is this completed variant of R motivic homotopy theory. And moreover, if you do a CP version of this, then you'll end up with, well, some other category. So that other category, that's the synthetic category, it's not motivic. It's just something else with an interesting comparison map. Okay, so first I'm going to say what does combine mean? And I think I can say this briefly. So roughly, given two filtered objects, you're going to take the deconvolution. So this has a a nice formula. So if I want to do this at the W spot, this is the colimit over x of I tensor y of j. So there's a well-behaved version, well-behaved way to combine two filtrations or two spectral sequences. Okay, so I think I want to say something about the homotopy fixed point spectral sequence, and okay, so why homotopy fixed point spectral sequence? I should label my acronyms. So basically, this is if I want to compute this completion. So remember, this completion is this mapping spectrum. You're going to compute this by filtering EG. So for example, there's a bar construction model for EG, and then you can filter it by skeleton. Although in the P equals 2 case, we like the S infinity sigma, so the infinite sphere with action is contractible and has free action, and we like that as a model, and it turns out to give the same spectral sequence. And okay, so the point is that this is computable. So maybe I'll just write what I said about the C2 case. We have a different model for EG that is this. And so the associated tower just breaks up this infinite sphere by its skeleton, and that has understandable quotients. So I can look at this tower. And one comment here is that this is the C2 plus based atom spectral sequence. So based on this, maybe it's not too surprising why the homotopy fixed point spectral sequence is showing up here. So the assertion is that if we want to understand the MU smash C2 plus based atom spectral sequence, all you have to do is combine the MU based atom spectral sequence with what we've now claimed is the C2 plus based atom spectral sequence. So maybe that's not so surprising, but the point is that you, by writing it as the product of these two spectral sequences, it becomes more computable. Okay, so there are a couple of variants of this. So you have to make some assumptions about X. So there are versions of the E2 page where X is so if X is MU are projective, then we get a nice, whoops, if X is MUR projective, then you get an E2 term for the mans that just looks like a combination. So the E2 page for the homotopy fixed point spectral sequence is it starts with group cohomology, and so this should look familiar. So you just have the group cohomology with coefficients in in ext. So this is one thing, and then if you also if X has trivial action, then you get a different form for the E2 page, and this. So if X has trivial action, then you can write this as kind of the other way around. So this is X over mu star mu with sorry, oops. I think I wrote this. Oh no, this is okay. So the homotopy fixed point spectral sequence is related to projective spaces, and so that's how this is turning up. Okay, but both of these things are very, very approachable. I guess if I'm doing this for the sphere, then I can just put it like that. Okay, and there are also comparison maps between the Mann's, the homotopy fixed point spectral sequence, and the ordinary Adams-Novikov spectral sequence. Okay, so I have like 3 minutes, and I do have one more thing to say. So I want to claim that this is this gives a new understanding of the C2 effective slice spectral sequence. So okay, so for any finite group, I have a slice spectral sequence. Famously used by HHR. I should also cite Duggar here. But it can be hard to compute. And at p equals 2 only, we have what is sort of regarded as a better slice spectral sequence. So there's in our motivic spectra, there's a motivic effective slice spectral sequence, and there's a Betty realization functor to C2 spectra, and whatever thing comes out of this Betty realization is the C2 effective spectral sequence. So this is more computable, and these two agree for certain spectra. So for p equals 2, they agree for say localized quotients of mu r, but not for the sphere. So for C2 sphere, the HHR slice spectral sequence is hard, but the effective spectral sequence has a very appealing E1 term. So it just kind of looks like Adams-Novikov-ish. So I'm going to write this in kind of a funny way. So the point here is that it's this is the C2 equivariant HZ, and if you have like a copy of Z mod 2 to the n here, then this is going to contribute a summand of HZ mod 2 to the n motivically, equivariantly. So it just kind of looks like the Adams-Novikov spectral sequence with coefficients in the C2 equivariant cohomology of a point. So Birkeland, Hahn, and Sanger show that for X is MUR projective, for example, the sphere. The effective spectral sequence is the décollage. So again, it's the shift of the MUR-based atom spectral sequence. So we have an analog of the MUR-based atom spectral sequence for odd primes, but after completion. So the upshot is that up to completion, the spectral sequence we produced, the CP MANS, is a CP version of the effective spectral sequence, which is something that didn't exist before. All right, that's my talk. Thanks for listening.